Hi, and welcome to our next subchapter here in our chapter on regularization. So this is on ridge regression. So here we will combine the linear model with the so-called ridge or L2 penalty, which will construct our first concrete regularized model here in machine learning. We'll also understand that the effect of including that penalty is resulting parameter shrinkage. So we'll see that parameters are shrinked closer to the zero origin. So fitted coefficients will in general be smaller than their unregularized counterparts. And we'll also understand the correspondence between regularized risk minimization and constraint optimization, which will help us to again understand a little bit better what really happens in the fit when we optimize the regularized form. And this procedure of this kind of mapping between the regularized problem without constraints and a constrained version, this will in general stay helpful in the future also for other forms of regularized models. Okay, so let's start. So do we even need regularization in a linear model? It's not super complex. Well, we've already seen it can overfit if P is just large enough and N is just small enough. Another problem you might have heard before in a lecture on linear models is that usually the OLS estimator requires a full rank design matrix. So if this has not full ranked, you have to do something about this. Of course, you can work with things like generalized inverses of your matrix, but also using regularization as a way around that is also very common. You might have also heard that for highly correlated features, OLS, so the ordinarily least squares estimator, so the usual way of fitting a linear model, becomes quite sensitive to random errors in our response, and this results in quite a large variance in the fit, and usually this is also noticeable in higher errors on test data in generalization. So what we'll now do is exactly what I've introduced before in the first part. So we'll take our linear model here, this thing, so this is our objective function, our ERM function, and we'll add a regularizer, a penalty to that loss. And the concrete penalty I will now add is the squared L2 norm of our parameter vector. Why do we do that? So we want to have some intuitive measure of model complexity, right? And some intuitive measure might be, that's what we're using here, the deviation from the origin. So if coefficients are close to the origin, they either have no, if they would be exactly zero, they would have no effect, or they at least have a very weak effect. So we now measure our complexity by simply measuring the distance, I should rather say the squared distance of our parameter vector to the origin. And by doing that, and including that as a penalty into the objective function, what will happen is now shrinkage to that origin. So parameters in the regularized fit will in general be smaller than their unregularized friends and counterparts, okay? And here in the formula, so I guess you can ignore the first part because that's just the usual ERM part. You should have seen this before. And here you see the squared norm multiplied by the control constant lambda, and here's just the longer form of writing down the same penalty, okay? Good news for that model, so for the linear model, under L2 loss and under the L2 penalty. So we have now two norms going on, right? So one norm to measure errors and one norm here to measure the penalty. And in this case, I've used L2 for both. For this specific type of regularized model, I can still analytically solve that, right? Good little homework exercise. Do that with pen and paper. It should take you roughly, 90 seconds to do this. Just compute the gradient, set it to 0, solve, maybe show that you're actually at a minimum by considering convexity. And then you get this formula here, and this really looks like our usual OLS estimator. The only difference is that before we invert x transpose x, we add lambda times the identity matrix to x transpose x. And this is also the origin of the name of ridge regression. So I don't know whether you know this. I'm not sure how intuitive that is, but the meaning of this is that we add small positive entries, exactly lambda, to this diagonal ridge of our X transpose X matrix, okay? And this is where the name comes from. So let's study the effect of this a little bit for a couple of very simple examples. So I've used an extremely simple data generating process here. So something that's actually linear, so 3 times x1 minus 2 times x2 plus some normally distributed errors, epsilon, and pretty obviously our true minimizer for that model here is, if I'm using a linear model, which I am, this is just 3 comma minus 2. These are exactly the coefficients read off from our data generating process. And yeah, I've also just for completeness sake, I've usually also copied over here the formula of the objective function we are now minimizing in rich regression. So what I've now plotted here is what actually happens with the penalized estimator when we change lambda from very small values to larger values. So let's start with very small values. So if lambda would be 0, right? Just exactly at the position of the unregularized model, which is simply then our estimator that we would get from an unregularized linear model. So it would get exactly this guy here, right? Now if we add, and the contour lines here in the background are exactly the contour lines of our unregularized objective, right? So this is where the optimum is, and this is where we end up if we set lambda to 0 in regularized fitting. If we now increase lambda more and more and more and more, you can see how we get pulled closer and closer and closer to the origin, right? So if you would now numerically look at the coefficients that drop out of this fit, they become smaller and smaller and smaller, right? They're closer to the origin, and this is exactly what I've claimed before. Now that this is the effect of regularization when we include it as a penalty into the objective. Here's a slightly different visualization. So here I've shown the contours of the regularized objective now, okay? So what happens now in the contour lines is something different. I'm not only plotting this guy, I'm plotting the complete thing. And the reason why I'm doing this, and I will do this again in the L1 subchapter, is that you can see how the unregularized objective it changes its shape, right? Because what happens now is that to this first part here, you now mix in this second part. So for rich regression, and the change is maybe not too drastic because you're actually using a quadratic form and mixing that with a different quadratic form, okay? Both of these guys here, first part and second part, are quadratic forms. Of course, they have different contour shapes or different Hessians, I guess I could say. So for this second part here, you basically have the identity matrix as a Hessian, right? So in a certain sense, everything becomes deformed, reshaped a bit more as circular contour lines, I would say. It is not super visible in the plots here. You will see this way more clearly when we are beginning to mix in different penalties like the L1. Again, I've plotted here the true minimizer of the unregularized objective function. So that's this red thing here. And, oh, sorry, no, actually, this is of course a nonsense. The green thing here is just the minimizer of the unregularized objective. And you can see that this does not move, right? Because, this isn't changed. It's not affected by, varying lambda. The red guy is the minimizer of the regularized objective, so the rich solution. You can see that because I'm plotting as contour lines now, the contour lines of the regularized objective, that always stays in the center of things, but it again moves closer and closer to the origin, what we have observed in the example before already. So, these were two very basic examples, just, running rich regression on a simple example. This is now a more theoretical consideration, looking at the rich objective function from a different perspective through a different lens. But this is, I would say, highly useful to really understand what happens in the optimization and how parameter shrinkage actually works and rich penalization actually works. So the problem that we have with kind of the examples here before, maybe remove a few of the scribblings. So if you look at this thing, yeah, this is now a mixture of two objective components, right? Like minimizing the loss, as I've said before, and penalizing the complexity of the model, penalizing the vector norm. And you have now two different functions mixed together and in a certain sense, overlaying each other, and it's not so easy to geometrically understand what happens here. It would actually be a little bit nicer if you could disentangle these two components and, I don't know, geometrically understand them in a separate fashion. And this is exactly what we are doing here. So we'll now understand the geometry of these two mixed components way better if we formulate the optimization problem as a constraint optimization problem. So we'll write down our ERM objective here as the objective of this constraint problem, and we'll write down our penalty as a constraint. Okay, so here the L2 vector norm, or the squared L2 vector norm of theta, should be smaller than some threshold t. So if Lagrange multipliers, you could actually see this as Lagrange multipliers in reverse. So take this problem here, take this constraint formulation and write on the Lagrangian of that, and you will see that you end up pretty much with this combined objective function here. Yeah? And so we're now doing this in reverse mode and using this to take the combined objective apart. So I haven't really talked too much about this threshold t here. So this really isn't the lambda, but there's a tight connection between lambda and t. So I'm not going into details here, but what basics also not so hard to see. There's a bijective relationship between lambda and t, and the thing is that the higher lambda, the smaller t. What I do want to do now is I want to look at the geometry of this constraint problem. So first of all, we can simply plot. Let me actually remove more scribblings. I guess we're interested in visualizing here our normal ERM objective. We've done this here. Yeah. So visualize the contour lines here. We've looked at something like this before, and in the middle there's our minimizer, so this would be our unregularized minimizer. Now, how do the constraints look like? So currently what we are saying is take the squared L2 norm of our vector theta, and this should not be larger than threshold t. Well, that's a circle, or that's the interior of a circle that we're describing here, right? So, and this is now the feasibility region of our constraint problem. So we are saying optimize this objective here, but please stay inside of this circle, okay? So we never can leave this blue region here. And the blue region will be larger if lambda is smaller and vice versa, okay? And this, I guess, helps us now to understand what really happens. So we could even now think a little bit about, even if we do not really know how constraint optimization works from an algorithmic perspective, we can approach this in an intuitive manner and think about how we would reach a solution here. So, and one way to do this would be to start from outside of the constraints. So we could start outside of the feasible region because we care more about, I don't know, the objective value. We really want to minimize that. So I guess we could start at the minimizer, right? But now we do look at the constraints and we are a little bit unhappy because we're actually at an infeasible point. Yeah, so that point is not valid. We can't use that. And what we can now do is we can jump to actually, this is not what is on this slide. So I'm an idiot. So I guess, I want to explain this here from a different direction. So, okay, so what we actually want to do is we want to start inside of the feasible region. Okay, so we'll start somewhere inside of this blue region to really have a feasible point. So and then we would be somewhere, for example, on one of these outer contour lines. Yeah, maybe we are here. And what we're now doing is we're jumping from contour lines to contour lines by moving more and more into the direction of the minimizer. Yeah? So we take the next inner contour line, jump to that, so like here. And then we go to the next one, go to the next one. So while we are doing that, our objective value becomes better and better and better. And because there's a risk, It's a loss error. It becomes smaller and smaller and smaller. And we do this until we become nearly infeasible. Yeah? So if the next, I don't know, epsilon jump would lead us outside of the feasible region, we stop. So then we would be here exactly on the boundary of our feasibility region. And this is where we stop. And this is where the, for this concrete lambda t combination, our regularized minimizer is located. Okay? So this solution path actually moves from the origin to the border of our feasible region in a certain sense with minimal L2 distance. We can also do this, and this is what I already started explaining before. We can also do this from outside of the feasible region. So we could start here as the minimizer, but this is not feasible. And then we jump to the next contour line. Now our objective has become worse. Okay, so getting a little bit more unhappy about that, but hopefully we're getting closer to the feasible region. And then we go to the next contour line, still infeasible, a little bit worse in objective value. We jump again to the next contour line, and here, then at some point, we touch the feasible region, right? And here again, we would stop, because jumping to the next contour line would make us worse. So why do that if you've already found a feasible point? And so here, the solution path would now move from the unregularized minimizer to the feasible region, again with minimal L2 distance. And here's our third visualization of the same thing. So before I've only looked at examples with a fixed lambda value, a fixed t value. What I'm visualizing here is the entire solution path for rich regression. So I'm visualizing what happens if I change my lambda values. So these cyan contour lines, now they indicate again the feasible regions induced by different lambda values. So the larger lambda, the smaller our circles are located around the origin. The red contour lines again shows our unregularized objective. And this path here is now what happens if I change lambda from 0 to pretty much infinity. And you can see how then again our shrunken solutions move more and more towards the origin, basically, until we end up, when lambda goes to infinity, in the 0 origin, with 0 coefficients. Last example here in this section, to show the shrinkage of parameters very clearly, and to also study them with a slightly more complicated model. So here I'll use polynomial rich regression. So I have a true function, this thing here, so that's a cubic thing. This is visualized in red below. And I'll use a dth order polynomial as I've done before, and I'll use d equals 10, so to start to overfit this data here, because you can see it's simulated from a cubic thing, right? So using way more orders of complexity than strictly necessary. And you can see this overfitting also a bit in the black line when I'm fitting to this data. Now, what we can now do is we can actually do exactly what I've described. So we'll, on purpose, use d quite large, although we know we might overfit now. But we will now add an L2 penalty to our objective and then solve the regularized problem. And what you can see here, well, in the table, but I guess it's a little bit nicer to start with the visualization on top. You can see what happens if I use different lambda values for regularization. So you use a 0 value, so this will just overfit with the unregularized polynomial regression model. That's the black thing. We've seen this on the slide before. So that's just this thing here copied over. And then a medium amount of regularization, lambda equals 10, and a pretty high amount of regularization. So you can also see what happens here in the table, right? And you can see that the fit, especially for the medium amount for the lambda equals 10, becomes better. At lambda equals 100, we might begin to over-smooth the model too much. We might begin to underfit. And again, you can also see very clearly here the effect of the coefficients, that the higher lambda is, the smaller our coefficients do become. Maybe these small guys here in the unregularized model are even being pushed to nearly 0, and they're being pushed out of the model. Okay, this finishes our section here on rich regression. Next section will be the lasso, or the lasso, if you want to pronounce it like that. See you soon.